Hello, I'm Ankit Patel, currently a third year student of engineering physics at IIT Roorkee, and I'm going to be talking about the experiment study of Hall effect. Basically, I'm going to be demonstrating how to find out the kind of doping in a semiconductor sample by the help of principle of Hall effect. So, here are the contents of this video. Firstly, we'll talk about the objective of our experiment. Then we'll talk about some background understanding of Hall effect to perform the experiment and deduce results. Then we'll make observations and make calculations based on the observations to actually make sense of the observations we get. And lastly, we'll talk about the results we get and we'll conclude the experiment. The objective of our experiment is to determine the kind of doping in the semiconductor sample given to us and find out some properties related to the charge carriers in the semiconductor sample, namely the charge carrier density and the charge carrier mobility. So now let's talk about the Hall effect. The Hall effect is the phenomenon of production of a potential difference called the Hall voltage across a semiconductor sample when placed in a region with applied mutually perpendicular electric and magnetic fields. So here is our semiconductor sample with thickness T along Z direction. The electric field is applied along X direction and the magnetic field is applied across the Z direction. And due to the Lorentz force acting on the charge carriers in the semiconductor sample, the separation of charges happen. One kind of charges, the positive charges, accumulate on one surface, and the other type of charges, negative charges, accumulate on the other surface. So due to the separation of charges, a potential difference is produced across the sample. So this potential difference is called the Hall voltage. So for Hall effect, we define a quantity called Hall coefficient, which is equal to Ey by Jx times Bz. And the Hall coefficient can also be related to the slope of the Hall voltage and current graph by this relation, and it can also be related to the charge carrier density by R is equal to 1 upon n times q. And if the electrical conductivity of the sample is sigma, then the electrical mobility of the charge carriers can be given by R times sigma. So now I'm going to be demonstrating the apparatus involved in this experiment.
So this is the whole setup for the experiment, the study of Hall effect. It contains various components. It has a Helmholtz coil. This Gauss probe we have to put in between the Helmholtz coil to measure the magnetic field by the Gauss meter. And these are the two p-type and n-type germanium samples. These this germanium sample is here, and it is, and to measure the uh, voltage and current across it, uh, this we are using the 4 probe arrangement. These 2 probes are for measuring the voltage across the sample, and these 2 probes are for measuring the current through the sample. And so in this way we can probe the current and current flowing through and the voltage across the n-type and p-type germanium samples. And it also contains a constant current power supply and a multimeter to measure the Hall current and Hall voltage across the germanium samples.
Now we'll calibrate the Gauss probe by measuring the magnetic field output with respect to the current applied by the constant current power supply.
To calibrate our setup, we'll use the Gauss probe. So we'll put the Gauss probe in inside the magnetic field produced by these Helmholtz coils, and then we'll see the variation of the magnetic field in the Gauss meter with respect to the change in the applied constant current. So we'll increase the current in steps of 0.5 and take it to 2.5. So as we can see, at 0.5, the Gauss meter reads 364, and at one it reads approximately the double of that. Um, so we can see that there is a linear relationship between the magnetic field and the applied constant current.
So here are the observations for calibration of Gauss probe. We can see that there is a linear relationship between the applied current and the magnetic field by the help of this graph. So we can see that the Gauss probe has a linear relationship. Now we are going to be seeing the demonstration of the observation of Hall voltage with Hall current for germanium samples by
To do
placing the
that,
germanium
we'll
samples in
calculate the
between
Hall
the Helmholtz
coefficient, the
coil.
charge carrier density, and the mobility of N-type and P-type germanium samples. So here is a P-type germanium sample which has four terminals. The widthwise terminals are to be connected with the voltmeter, and the lengthwise terminals are to be connected with the ammeter, and then we'll place this Hall probe inside this magnetic field to to find out a variation of the Hall voltage with respect to current. So I'm going to connect this terminals. So these are the widthwise terminals, as you can see here. So these bitwise terminals are to be connected with the voltmeter to measure the Hall voltage, and these lengthwise terminals are to be connected with the ammeter to calculate the current. So while placing this four probe, one should be very careful about the arrangements. The four, neither the four probe nor the this Gauss probe should touch either of the Helmholtz coils. So okay. So now to record the variation of Hall current and Hall voltage, we'll set the magnetic field at some constant value. In our case, it's around 250 watts. So we'll increase the Hall current in steps of 2 milliamperes and record the Hall voltage, and then plot a graph, and from the slope of that graph we'll get the Hall coefficient. So let's increase the Hall current in steps of 2 milliamperes. Similarly, for finding out the Hall coefficient and other related properties, namely charge density, charge carrier density, and mobility of an N-type germanium crystal, we'll place the N-type germanium crystal photo inside the magnetic field and see the variation of Hall voltage with respect to Hall current by maintaining a constant magnetic field, and plot a graph between Hall voltage and Hall current and get the Hall coefficient from that graph. And it's important to note that as the Hall voltage was increasing with Hall current for the P-type germanium crystal, it will decrease with increasing Hall current. So the Hall coefficient for P-type germanium crystal will be positive, and the Hall coefficient for N-type germanium crystal will be negative.
So here are the observations for Hall voltage for a p-type germanium sample at the constant magnetic field B is equal to 250 Gauss. We can see that the Hall voltage increases linearly with the Hall current, and so from this table we can deduce that the slope of the graph between Hall voltage and Hall current does not vary, which means the Hall coefficient is constant for the sample in this range of applied current. Here is the graph between the Hall voltage and Hall current for a p-type germanium sample, and we can see that it's fairly linear. So here are the observations for Hall voltage for a n-type germanium sample at a constant magnetic field B is equal to 250 cos. We can see that it's varying linearly with the Hall current, but it's decreasing with respect to the Hall current, unlike the p-type germanium sample. So from these two graphs, we can see that the Hall coefficient is positive for a p-type sample and is negative for an n-type sample. So here are the calculated values for p-type and n-type germanium samples. We can see that these values are very close to the theoretical values. Specifically, the values of charge carrier density are easier to look at, and we can see that those are very close to the range of theoretical values. So from our experiment, we found out that the value of Hall coefficient is positive for p-type semiconductor samples and it's negative for n-type semiconductor samples. And we found out the charge carrier density and carrier mobility for both the type of samples, and those values agree with the theoretical values. And we also noted that the values of Hall coefficients do not change for the range 0 to 10 milliampere Hall current for both the samples. Thank you.